As a group, we quickly came to the decision that we wanted to test an object in the wind tunnel, and what better idea is there apart from bullets? Their whole principle is their aerodynamic shape, and we wanted to experiment with this. We wanted to find the ideal shape for a long-distance firearm. Our predictions were that the pointed tip with a boat tail would have the least drag. We also predicted that a boat tail compared to a flat base would have less drag, as their drag coefficient showed this. These predictions were made with the ballistics coefficient equation. A pointed tip compared to a rounded tip would give a higher ballistic coefficient value, and a higher ballistic coefficient value would give a bullet a more stable flight with better accuracy and range.
When the bullets were created on CAD, they included a 4mm hole that was machined to 6mm, and then the holes were threaded so the bullets could be fastened onto the mounting rod.
You were doing alright last time, mate.
The mounting rod is tightened into place with the angling of it set to 0, so it's set 90 degrees to the vertical. The models were secured horizontally by the use of a 90-degree tool.
Oh yeah, I can't do it.
As you can see from our results, we were correct in our hypothesis in the fact that the sharp-pointed boat tail bullet would prove the most aerodynamic and showed the least drag force out of all of them. You can also see that both of the rounded tips on average were worse than the pointed tips, just as the boat tails performed better than that of the flat base. One reason for this is due to the boat tail added to the end of the bullet. This is significant because on an original flat base bullet, as the bullet speeds through the air, it leaves a small vacuum pocket just on the end. And as this collapses, the nearby air and back of the bullet experience a force which helps to drag the bullet back. The reason why a boat tail is so effective is due to the shallow angle it takes off the end as it works down the circumference, allowing it to occupy most of the space which would have previously been a vacuum. As you can see from the paper, I also decided to calculate the Reynolds value for the end point of the bullet, which is 146mm from the start. I calculated this to be 342,000, which is well above the 20,000 required for the boundary layer to be turbulent. I then decided to find out where the transition region would lie, and I found that between 8 and 9mm in, where it goes from 18.7k up to 21k, which obviously exceeds the 20,000 needed for the boundary layer to become turbulent.
Our results were successful in the sense that they showed the same pattern as real bullets, this being that the coefficient of drag for the pointed tip with boat tail was the smallest, and this matched our prediction. However, our calculations for coefficient of drag are not near the coefficient of drag for real bullets. This is understandable as the wind tunnel cannot get up to speeds anywhere near that of which real bullets will be travelling.